Okay, so here we are, matrix operations, chapter 2. So chapter 2 deals with what's called matrix algebra. And, you know, the way we denote a matrix A, okay, is it's often convenient to denote a matrix A in terms of a vector with column vectors. Okay, so take a look at it. All right, and let's see here. So they mentioned just like if you have well, they talk about just what diagonal entries are of a matrix and so forth. And I think it'd be easiest just to go and honestly look at a few examples here. So one moment, let me get there. I want to make sure. Yeah, okay. Let me get there here. Let me go down here a little bit. Yeah. All right. So before we get to example 1, a general matrix A has m rows and n columns. And if we want to denote the elements of the matrix with like symbols, like this matrix here, figure 1 matrix notation. Okay, this here, we denote that element of the matrix as A sub 1, 1. And why do we do that? Because that number is in the first row and the first column. Okay, so that's how we denote that entry in the matrix. It's the entry in the first row and the first column. This entry here, that entry there, is in the first row and the jth column. If we only need 2 numbers for the matrices, because if you had 3 numbers, you would have, that would be a matrix in 3-dimensional, like sort of a 3-dimensional space matrix. Generally speaking, the matrices that I've seen in applications just have a certain number of rows and a certain number of columns. I've not seen a matrix that has rows, columns, and then another, I don't know, dimension to it, to be honest. But you can look that up. You can look that up, Mikhail. It would be interesting. It would be certainly interesting. Right now, let's focus on the 2-dimensionals. So here's example 1. Okay, example 1. And they're defining matrices A, B, and C as you see them there. And the matrix A plus B is defined. Well, Mikhail, let me get back to you on that, okay? I'll get back to you on that. We can talk about that after class. Not a problem. So there's a matrix A, there's a matrix B, and we can add them because they have the same number of rows and the same number of columns. So you can add matrices if they have the same size. Okay. You can subtract matrices if they have the same size. Okay. But notice, so the matrix A plus B, to add those matrices, you just add the corresponding entries in A and in B. But the matrix A plus C in example 1 would not be defined because matrices A and C have different sizes. Okay, are there any questions on that? Okay, well, let's talk about example 2 now. What if you have a matrix B, and we're sticking with the matrix B above, and you wanted to multiply the matrix B by a scalar? All you would do is multiply the entries of the matrix B by 2. Easy, not hard to do. And then, you know, you can do all kinds of other types of things. You can take A minus 2B and all. I mean, basically, it's pretty intuitive. There's a theorem. There's a theorem here, theorem 1, that, hold on, I'm sorry, theorem 1, that gives you some of the some properties of matrix algebra. Now, of course, another very important idea is being able to find a product of two matrices. And for that, let me go to a little example that I have here that you can copy in your notes. Let me give you a moment to copy. And while you're copying, let me ask, could we add these matrices A and B? Or could we add them? No. That's right, Mikhail. That's right, Bill. And because they're different sizes, The matrix A, okay. Hold on here, one moment. Okay, sorry about that. So the matrix A is a 2 by 2 matrix, 2 rows, 3 columns. And the matrix B is 2 rows with 3 columns. And the product, the matrix product A times B, is defined because if the number of columns of the first matrix and the number of rows of the second matrix matches, okay, then A times B is defined. And in fact, let me just write this down here. A is a 2 by 2, B is a 2 by 3. So the product matrix would have dimensions 2 by 3. Okay, so the matrix multiplication is defined because the number of rows, the number of columns of the first matrix equals the number of rows of the second matrix. And when you get the product matrix, it's going to have to be a 2 by 3 matrix, 2 rows, 3 columns. How many maybe recall this from another class? I think Mikhail said he recalls it. How many do any of you recall doing matrix multiplication? Okay, Marcella recalls it. Well, how do you do this? All right, there are several ways we can do the matrix multiplication. 2 methods, really. One method is called the row column rule. The row column rule. Yes. Sure, Mikhail. Sure. And what is the row column rule? Well, so let's take a look. Okay, all right, no problem. Let's take a look here at the, so again, this is a 2 by 3 matrix. The entry in the first row and the first column is A sub 1, 1, right? That's the entry in the first row and first column. To get that, you have to take the first row of A and the first column of B, and hold on, okay, and multiply them together. But you see, you take the 2 in that row and multiply the 4 in that column, 2 times 4. Plus, you take the 3 in that row and multiply by the 1 in that column. So you get 2 times 4 plus 3 times 1. Let's take a look at this entry here. Let's take a look at this entry here. So this entry is the entry that's in the second row and the second column. Okay, so in order to get that, you have to take the second row of the first matrix and multiply those numbers by the numbers in the second column of the second matrix. So 1 times 3 plus 5 times -2. Okay, that's why we call this the row column rule. And that's, I'm sure, the rule that you have seen earlier in your life, some of you. Okay, it's coming back to Mikhail. Good, good. Let's do one more. Let's take this entry here. This entry here is the entry in the second row, third column. So to get that, you have to take, no, I'm sorry, it's the first row, third column, right? First row, third column, right. So you take the first row of A and the third column of B and multiply as you go. 2 times 6 plus 3 times 3. And you'll get your 2 by 3 matrix. That's called the row column rule. That's called the row column rule. Are there any questions on that? All right. Well, let's look at another way to multiply a matrix by a matrix. And for that, we're going to rely on a definition. Okay, so if you look at the top there, method 2, I have a definition of the matrix A times the matrix B. Okay, it will equal the matrix with those column vectors, A times the vector B1 plus A times vector B1 is the first column, A times vector B2 is the second column, and A times vector B3 is the third column. And the vectors B1 and B2 and B3 come from those are the column vectors of matrix B. Now, what I want to do is show you how the row column rule that you just learned is equivalent to this new definition for matrix multiplication. And that definition is on page 97 in the textbook. Let me just, maybe I'll just hold on here one moment. let me just go to the book real quick here. We'll come back to this. Let me just go to the book so I can show you this. Don't worry, we're coming back. We're coming back. This is another way that you can multiply two matrices. And this is the definition that we're using for this second method for multiplying the matrices in our example. I just wanted to be in the recording so you could see it. So now going back to the problem here. So what I've done here is I've written out the row column rule that you just learned. This is the row column rule. And you'll see that the row column rule is equivalent to the approach that they're talking about above. Because if you take the matrix A times the vector B1, using the row column rule, that would equal what you see here, which gives you the first column. If you take the matrix A times the vector B2, okay, that's a 2 by 2 times a 2 by 1, right? So that will give you a 2 by 1 vector. That's what you're going to see here. Okay, and then the matrix A times the vector B3, which forms the third column, well, that's equivalent to the third column vector using the row column rule. So really, when you're doing the row column rule, when you're getting those column vectors, you're really just doing A times vector B1 to give you the first column, A times vector B2 to give you the second column, and A times vector B3 to give you the third column. That's all you're doing. And so you end up getting the same product matrix. Absolutely fascinating, really. And you could denote it using this as shown here below. The matrix with column vectors AB1, AB2, and AB3, and that can be represented using this notation, where you're really what you're doing down here, right? If you want to think about it, is you're multiplying A times the vector B1, A times the vector B2, and A times the vector B3. I mean, it's just notation, really. Pretty cool, huh? Pretty cool. So now you've seen matrix addition. Yeah, you've seen matrix addition, matrix subtraction. You know how to do matrix multiplication. Okay. And let's see here. Let me just go a little further here in section 2.2. Go back to the book. I think we're all good here. So theorem 2 in section 2.1 gives you just some properties of matrix multiplication. And it's common sense. Matrix multiplication is associative, it's distributive. If you take the identity times the matrix A, that's that rule E, you'll get back the matrix A. To sort of see that real quick, that last rule, again, it helps to do an example. It helps to do an example to make it clear. If you had like a vector I2 times a matrix A, okay, well, that would be 1, 0, 0, 1. That's the identity matrix for a 2 by 2. And let's say the entries in the matrix A are A, B, C, and D. Okay, so using the row column method, you'd have 1 times A plus 0 times C for the entry in the first row, first column. And then you'd have, for the entry in the second row, first column, 0 plus A plus 1 times C. And then for the entry in the first row, second column, you'd have 1 times B plus 0 times D. And then the second row, second column entry would be what? It would be 0 times B plus 1 times D. And that will give you A, C, B, and D. Okay, so you get the matrix A. It's kind of like if you take 1 times 3, you get 3. If you take 3 times 1, you get 3. So analogously with matrix multiplication, the identity matrix is, if that's the matrix that has 1s along the diagonal, it's a square matrix, meaning it's a 2 by 2 or 3 by 3 or 4 by 4, and then 0s everywhere else. Okay. Are there any questions? Okay, then let's continue here. Let's continue. Something that's some warnings here. The average person doesn't know this, but A times B is not equal to B times A when A and B are matrices. Now with numbers, it's true. 2 times 3 equals 3 times 2. But with matrices, matrix multiplication is not commutative. It is not commutative. Okay, so that's, I'm sure that'll come up in your multiple choice, true, false kind of questions. All right, and you can try it for yourself. Just try it. Take a, well, actually here in example 7 above, they show that. They give an example. See, if you find one example that disproves something, hold on here. Hold on. Now wait, I lost my book. Hold on. Yeah. So see, A times B is not equal to B times A. Matrix multiplication is not commutative. Example 7. You find one counterexample, and you've basically shown that that matrix multiplication is not commutative. All right, let me keep going here down a little bit. Okay, powers of a matrix. Sometimes this comes up. If you have A and you raise it to the kth power, That's just the matrix A multiplied by itself k times. But it's only true if A is a square matrix. It has to be an n by n matrix. It has to be square. Okay. And also another common thing is the transpose of a matrix. So transpose of a matrix, okay, is denoted by A with the superscript T, A transpose. So what happens is, to get a transpose of a matrix, is you, like you see there, when A equals A, B, C, D, A transpose is A, C, B, D. So what happens is, the rows of the matrix A, you make them the columns in the transpose. That's what happens. So like the matrix B, if you look at the matrix B, if you were to take the rows of matrix B and turn them into the columns, they would be, that would give you B transpose. So do you see there in example 8 how we get the transposes? Michaela, transpose is not a reflection. It is not a reflection. I see what you're thinking. You're thinking for a 2 by 2 matrix. In some case, well, if you go to, I want to be careful how I answer that. In very special cases, it could be, I just want to be careful how I answer that. We generally don't think of a transpose of a matrix as a transformation. We think of, but I'm not saying it can't happen, okay? I mean, I want to say it the right way. I'm not like, we're not worried about that right now at the moment. But if you understand example 8, then you understand about transposes. And transposes actually have properties, and theorem 3 gives some properties of transposes. And you can verify those properties. Like, for instance, the last property, theorem 3D, says that the transpose of the product A times B equals B transpose times A transpose. That you can prove. You can prove that to yourself. And in the homework, actually, you'll have an opportunity to do that for section 2.1. That's really, those are the key concepts behind the section 2.1. And I'll make one more comment, because I know it is 8:45 now. Numerical notes. Okay, so there they talk about the fastest way to multiply matrix A times B on a computer depends on which way the computer stores matrices in its memory. So we're talking if you have matrices A and B, and they're huge matrices, okay? And the second column says the definition of A times B lends itself well to parallel processing on a computer. Columns of B are assigned individually or in groups to different processors, which independently and hence simultaneously compute the corresponding columns of the matrix product A times B. Are any of you familiar with parallel processing on a computer? Any of our computer science majors here? Have you worked with that at all, or heard of that? All right, Mikhail says it sounds familiar. All right, and okay, well, great. Are there any questions before I stop the recording? Okay, all right. Well, and Mikhail thinks he's seen that. All right, well, this will probably come up later on then in your computer classes. Okay, let me stop the recording then. Excellent.